Thank you. So are there negative masses in nature? And if not, is it just an accident, or is there a fundamental principle forbidding them to be assembled? So this is the questions we want to have a clear picture of. And of course, the idea of pondering about negative masses is very old. Already in the 50s, Monty came up with a fully general relativistic argument showing how problematic having both sides of masses can be. But we can get a hold of what it means just in a Newtonian regime. It's enough to get a good understanding of his argument. So you imagine you originally at rest, you place two masses, one positive and one negative. And because they have opposite signs, the force will be repulsive, just like a pair of electric charges with the same sign. Unlike the charges, however, the negative mass will respond to the force anti-parallelly, and the negative and the positive mass, the acceleration will be parallel to the force. So the result of that is a pair of self-chasing, accelerated pair of masses changing after one another in an accelerated fashion. Of course, this is not violating any fundamental conservation rules. For example, if you release them from the rest, it will remain with zero momentum at all times. But it's not disastrous, but it's mischievous. So it suggests that they are not around, if they are, they're not widespread. But we can still ponder why we can't build them. So if we use attractive forces, we can keep reducing the mass of the combined system if you start off with components with positive masses. So this is, for example, an atomic nucleus. You can see this plot. You have the average binding energy per nucleon as a function of the atomic number. And unfortunately, nuclear physicists like to flip the sign of the binding energy. So this is, in our convention, minus the binding energy. So you see that every time you add a nucleon, for example, close to iron, which has the minimum value or the maximum in this convention, you have to subtract off from the system some energy. So you could think, in principle, you could do that and exploit this to the extreme, to which you get zero energy or even negative mass in the end. Of course, as you can see from the order of magnitudes of the mass of the nucleon and the mass and the order of magnitude of the binding energy, that the atomic nucleus is not a good idea to pursue this. And in fact, there are very general results from late 90s, sorry, 80s, early 90s, basically saying that in classical physics, as long as you have an asymptotic flat space-time, you cannot get negative masses in anything like this. So this program is flawed. The least mile of the assumptions of these theorems is the dominant energy condition on a certain initial value surface. So this is not, so the dominant energy condition, as you know, it's just an assumption that can be translated by saying that energy fluxes ought to follow future-directed timeline curves or causal curves. And these are verified in any classical field theory that we need. What I mean is you can write down a classical field theory for which the dominant energy condition is violated, but these theories would be artificial in some way because you don't need, so for all matter we know to exist, our classical models of them obey the dominant energy condition. So if you want to concoct a system possessing negative mass, you have to go to quantum mechanics, where the violations of the dominant energy conditions are ubiquitous. And here is a blatant example of a static violation of the dominant energy condition. It's the Casimir effect. So the idea is you start from imposing boundary conditions emulating the perfect conductive planes on the quantum electromagnetic field, and you can compute the regularized stress energy tensor of this configuration. And the result is known for a very long time, and is what I write here in this slide. So you can see that so first of all, it is zero everywhere except for in between the plates. And the energy density there is negative. So if you were to integrate this energy density over all space, you're going to get a negative number. So before going what's wrong with that, we have to ask, is it meaningful to integrate the energy mass over all space to try to come up with a mass? Well, and this is a very subtle issue. So the masses of extended bodies is not as straightforward as a point particle in Newtonian physics. There are many things on which the results of, so if you try to hang a system on a dynamometer and read the result, this number is going to depend on many things that are not properties of the system itself, but of the interaction. For example, what we even mean by a uniform gravitational field. Is this body rigid? Is this notion of rigidity compatible with general relativity? Where is the dynamometer reading? Is a point of suspension? Is that infinity? Is that an integral? All that. So instead of trying to come up with an answer for that, we decide to use active gravitational mass of the system, that to say. So you use a test particle at infinity and measure the gravitational pull of that particle. So if you were to keep that at rest, if you're stationary, so the trajectory will be accelerated. So you can read from that the Komar mass, which captures this idea of active gravitational mass. So in order for it to be defined, all you have to do is having a stationary space-time, and it's written as an integral over a topological two-sphere at infinity, at far distance from the bodies. Now, if you want to understand how this mass is composed of, we have to write that in terms of the matter content. So if you believe in Einstein's equations, and in the interior of this surface that I denote by the symbol of infinity, there are no holes, then you can convert this integral to an integral over the interior of this surface plus the surface itself, and write that in terms of the energy momentum tensor. And what you get is not exactly the Newtonian formula, but if you, of course, if all the pressures are small, it's how you recover the Newtonian formula. This gives back the integral of the energy density. Of course, in Casimir effect, this is absolutely not in the Newtonian regime, because as you remember, the pressures are the same order of magnitude of the energy density. So you ought to do something better. And we can, if the system is isolated and we treat gravity as a linear approximation. So we're in linearized gravity in Minkowski spacetime. And if the full energy momentum tensor has got zero divergence, then, and furthermore, it decays to infinity more rapidly than 1 over r to the 3rd power. So now the plates are thought to be finite, but close together, so we can neglect any edge effects and so on. So then you can show that these integrals are zero. So if you plug back to that formula, then you end up just having the integral of the energy density, which is the same as the result for the passive gravitational mass, for example, if the size of the body is shrink down to a point. So the last thing that we need to address in order to justify the use of that formula, the naive formula that I referred to, is, well, is it legitimate to take the brackets of this T naught naught and say that this is how space-time responds to? And you might rightfully think that's not the case, because the energy density used as an operator is very far from a C number. You can show that the expectations of this variance is the same order of magnitude as the expectation value of T naught naught itself. So rightfully so, you can say that well, I don't know how a point mass gravitates around such a system. However, as long as we are sufficiently far from the system, so we are probing that from infinity, we are only sensitive to the monopole approximation. And in that approximation, that operator whose expectation value gives is our, we are tempted to call that the mass, it coincides with Hamiltonian. And by definition, vacuum state is an eigenstate of that. And this integral doesn't fluctuate at all, despite this T naught not being very operator-like, not the spatial integral. So this is all to say that that naive formula is reliable in linearized gravity around Minkowski background. If it's not Minkowski, you can use the same arguments, but not neglect the pressures as we were discussing before. And you have to verify the coincidence with Hamilton. So if that's so, we still have a problem. So what's happening there? Does a Casimir apparatus possess negative mass? Well, the trick is the electromagnetic field cannot exist in isolation in that state. And there are many ways of convincing yourself, the most straightforward of which, you can just compute the divergence of the stress energy tensor and verify that it's non-zero wherever the plates are. Alternatively, which is one that it's more useful to us, which is just realize that there is a discontinuity between the ZZ component of the stress energy tensor across the boundaries. This translates into a force, which is the Casimir force between the plates. Well, this means that if you leave them alone, the system can't be in equilibrium. So it cannot be static, and this whole discussion falls apart. So we need to introduce something else. So one way would be, well, we just complete the system in order so that the full system is in isolation. Another way, which is, well, we need to add struts to the system. And the function of these struts is to balance out this attractive force between the plates, to balance out the Casimir force, right? And so they have to provide the force that is TZZ in the interior times the area and integrate that. You can distribute these struts as however you want. And now, the whole game is how I can fabricate the system so these struts are not to be complicated contraptions that you can imagine using quantum devices, because then I'm just pushing the question forward of how you create that matter in the first place. So if the struts are classical, it's very reasonable to demand that these struts obey the dominant energy condition. And so that imposes a limit on how light they can be. And as soon as you accept that, and you include the struts into the system, and you calculate the mass, you obtain a positive result. Furthermore, you can show that if instead of the Casimir vacuum C, you've got a different state which preserves the staticity of this stress energy tensor, then you can show, well, this inequality just follows from quantum energy inequalities, and so they are basically for free. And you can show that these results persist, even if you're not in the Casimir vacuum. So one thing to stress is that all we demanded, so the system already has positive energy, and the system only has the electromagnetic fields and the struts. So you might say, well, the struts are not responsible for placing for the dynamical treatment of the boundary conditions. So besides that, you should have plates. And yeah, I agree with that. But notice that they play no role in the positivity of the mass, which is a very interesting result to my eyes. Now, turning back to the more general inspection of the possibility of constructing negative energies, this slide is just to show that you have to have certain assumptions. For example, this is the family of Morris-Thorne geometries. They're static, and you can calculate the Komar mass from the definition of that integral over the two sphere, and you see that it can have any sign depending on how the redshift factors depends on the position. But if you impose on asymptotically flatness, you don't need to define the bound. Yeah, if you impose starting asymptotic flatness, then this notion ought to coincide with the ADM mass, and that is shown to be positive just by the definition as well. Furthermore, you have to have regularity, right? So if you have native singularities, then of course you can violate this result. So yeah, the takeaway is we really don't know how to construct negative masses in semiclassical gravity. So I'd like just acknowledge that this work has been performed not in my current institution, so I acknowledge my collaborator, George Martas, and my host institution. And of course, thank you all for listening.
Okay, thank you. Thank you for your participation in this workshop with this nice talk. It's time for questions or comments. Any question? Gerardo García. Gerardo.
Hi, thanks for the nice talk. Are you familiarized with this quantum interest conjecture, in which it, roughly speaking, so this is like a stronger version of that conjecture, right? What you are pursuing here, like.
Well, yeah, well, okay. So this quantum interest conjectures, well, I think they have been proved. Well, so you can use quantum energy inequalities and prove certain average energy conditions, and they can be interpreted as in terms of, as Ford has mentioned, as this quantum interest. They are local and they are probing along causal curves. It's a lot different here because here we're interested in these spatial integrals. So so that's one mindset. So and that's interesting for many reasons. One of which is how the first idea is how can we generalize, can we relax the positive energy theorems to include certain averages, inequalities that we know to exist in quantum field theory. So that's one question, and that's you can do that for singularity theorems. Why can't you for this type of and that's very it turns out they don't exist in these spatial averages. So it's very different for that reason. So and here, and I notice that here we are in this placing boundary condition. So this average integrals are not satisfied. Right? For example, the average null energy condition is not verified in this Casimir setting, right? For the electromagnetic field.
Okay.
Okay.
Thank you.
You have another question from Sebastian Schuster.
Yes, and your previous answer is actually quite connected to my question. Namely, did I understand it correctly that most of this was concerned with the dominant energy condition when you also have some results for the averaged energy conditions?
You mean this slide?
Well, it's more general question because you started off from the dominant energy conditions, right?
Right. If the dominant energy condition is verified and an initial value of surface, then we can apply this positive energy theorems. Yes.
And so also when you were working with the struts in the Casimir effect, right, it was also with the dominant energy condition, right?
Only struts. Yeah. You don't need to say anything about the field, of course. Yeah, that's right.
So given that you're working with the quantum model, why focus on this pointwise energy condition when there's also technology for the averaged energy conditions? Right.
No. Yeah. Well, yeah. This is connected to my previous answer. So you could, but in the so everything is static here, right? So if you imagine integrals over time-like curves, they don't tell you much more because everything is static.
In some sense, they would, because you would expect that because you have quantum fluctuations, that the pointwise energy conditions might not pick up the right thing. Like the fluctuations might be part of the problem, and part of why people consider the averaged energy conditions is to have some more careful approach to how these fluctuations influence the things.
Right. Yeah, I entirely agree. So, but again, if you're interested in finding the mass and you believe that the mass is sensitive to the expectation value, then this fluctuations don't appear. But you're right in principle, right? Yeah, I mean, yeah, this is whole business. We don't know. We don't have an experiment saying how this fluctuations gravitate. Right? So this has been discussed in this workshop already. So yeah, I mean, yeah, I'm open if you have ideas of yeah, if you have an idea of how this all behaves, I'm very glad to hear. Yeah.
Sure. Let's maybe discuss on Slack, but that already helped understanding the context a bit. Thank you.
Okay, thank you.